So we're going to start with chapter 1, and we're really going to talk about chapter 1 and really chapter 2 today. There's not much in chapter 1, but we are going to talk about a few things that you'll be responsible for. A lot of chapter 1 sort of introductory type of things, but some stuff about the scientific method we'll talk about a little bit, and we'll talk about some matter and stuff like that. And the majority of our focus will be probably mostly on chapter 2 and get into some of that. So let's start with chemistry. Chemistry really does impact all areas of our life. We do think about obviously chemical reactions, but chemistry is involved in manufacturing of new products, obviously medicine, even things like food, makeup. There's all kinds of places where chemistry really comes into play, including fireworks, which is chemistry in action. Why you get the different colors when they explode, because there's different elements in there. Electrons are being excited, all those fun things. And we get to see all these pretty colors. So a lot of what we deal with in terms of chemistry really does deal with matter. And matter, as we'll talk about, is essentially anything that sort of occupies space and has mass. So that's pretty much everything. And a lot of what we deal with in chemistry is the different states of matter, and as they sort of maybe transition from one state to the next and what happens. So when we talk about states of matter, there's really three sort of states that we oftentimes deal with a lot in chemistry. There is the solid state, there is the liquid state, and there is the gas state. And in the solid state, typically speaking, things are packed in relatively tight to one another. They really don't possess a lot of energy, which means they can't really move past each other. And that's why they sort of lock into a rigid type of environment and are really hard, usually, solids. Now, when we get to the liquid state, we still have everybody that is still packed in there relatively close to one another, but they actually have a little bit more energy, which means they actually do have enough energy to sort of, slide past each other. And that's why when we think about liquids, they're fluids, right? You can pour them, right? They flow out and stuff like that because they do possess enough energy to basically move around. When we get to the gas phase, at that point, everybody has completely broken apart from one another. So as they're flying around, they obviously have a lot of energy at this point. As they fly around, they start to collide with the walls of the container. And as we'll talk about when we get to the gas chapter, we associate pressure with gases. And that's a result of how many collisions sort of occur as they are flying around with all this energy. So a lot of what we deal with in chemistry involves matter. It involves the different states of matter here. And a lot of what we look at also involve the changes of states. So when we go from something like solid to liquid, that's the process of, what is it? When you go from solid to liquid, it is, if I take an ice cube out, it starts to melt. Yeah, so that's the process of melting. You feel bad about the melted ice cube, you put it back in the freezer, and your liquid water then goes back to solid in the process known as freezing, right? So that is freezing. Yeah, thank you. As we go from liquid to gas, so that is the process of evaporation or vaporization. Going from gas back to liquid, that's the process of condensation. As you go from solid, skipping the liquid phase and go to gas directly, that is sublimation, like dry ice. If you've ever seen dry ice, which by the way is not water, is carbon dioxide. Dry ice goes from solid to gas, no liquid cleanup in between along the way. You also can go from gas back to solid. That is the process known as deposition, like you're depositing something on something. So CDs, DVDs, if you even know what those are, you can Google them, I suppose. They're shiny. That's how they get them shiny. They actually deposit metals on top of them through the process of deposition. So a lot of what we look at in some of these chapters, and we'll deal more with this in a later chapter, is these transitions and what's occurring during these transitions. And it also involves a lot of times energy is a big sort of factor of what we look at, what is happening in, say, a chemical reaction. And there's really sort of a couple of processes that will occur in terms of energy. And one process is energy has to be released, and another process is energy has to be absorbed. So if we were just to look at sort of these phase changes as we go from, say, solid to liquid to gas, would I need to put energy in to do that or remove energy to do that? Energy needs to go which way? Yeah, energy does need to be put in. So if you think about the ice cube example, we take the ice cube out, it picks up all the energy from the surroundings, right? It starts to melt, becomes liquid water. You want to make pasta, right? You take that liquid water, put it on the stove, put some fire underneath it, right? You heat it up, absorbs out of energy, the water starts to boil, and that's the water going into the gas phase, right? All the steam that's happening. So all that process there as you go from solid to liquid to gas, those are all processes where energy is absorbed, and those type of processes are what are referred to as being endothermic. So an endothermic process is one where heat and energy is basically being absorbed. A lot of times we think about energy, and which is thermodynamics, and the idea of like system and surroundings. So either a system is absorbing the energy or the surroundings is absorbing the energy. The opposite would be true if we go the opposite way from gas to liquid to solid. We have gas molecules that are flying around really fast. They have a lot of energy. You need to really remove the energy from them. So as you remove the energy from them, they're going to fly around a lot slower, which means when they come in contact with each other, they no longer have enough energy to escape, and they kind of clump and drop into the liquid phase. You continue to remove the energy from that, they no longer have enough energy really to boom past each other. They lock themselves into the solid state. I'm sure whoever's teaching over there is enjoying me knocking on the door. So those are all processes where energy is released. And those processes where energy gets released is what is known as being exothermic. So exothermic is when energy is released. Endothermic is where energy is absorbed. And a lot of times we do look at reactions in chemistry in terms of energy. And we have a whole chapter on energy coming up in a few chapters down the road where we'll talk about all this. And sometimes we're given a chemical reaction and really like an energy value. And oftentimes we can basically display a reaction as being either endothermic or exothermic by the actual value we see for energy. And we'll talk about it a little later on, but delta H, which is the enthalpy, which is basically a fancy word for the heat of a reaction. Yeah. When solids become, no, so that would be endothermic. You got to put energy in there to get them to the gas phase. Going the opposite way, if you go from gas to solid, it would be exothermic in that case. Yeah. Other questions? So enthalpy is a fancy way of saying basically delta H, which is what the little triangle means, is the change in enthalpy. It's a fancy way of basically describing the energy of a reaction. And typically speaking, if you see an energy value for a reaction and it is positive, doesn't really matter the number, but if the value is a positive number, it's an endothermic reaction or value. And if you get an energy value that's given to you and it's a negative number, it represents a exothermic sort of process. Any questions on that there? And obviously we'll talk a little bit more about this as we continue on. Now, another important sort of aspect of sort of science in general is the idea to solve problems. And a lot of times this is the scientific method. And really, most of the scientific method and most of investigations and experimentations usually starts with some type of observation. So you observe something, and maybe somebody you work with observes something, and you go, "Wow, that seems interesting. I wonder why that sort of happened." And what you typically want to do in sort of the scientific method is to come up with what is referred to as a hypothesis. And that's really a tentative sort of explanation of really what is happening and why you're observing what you are seeing. A really good hypothesis is something that you can test. So a lot of times in chemistry and science in general, we like to have hypotheses that we can test and maybe verify or not verify. And usually what will happen after you sort of formulate a hypothesis, you will perform an experiment. And you will perform an experiment. And I would say probably in most cases, what happens is you make some more observations, and then you go tell whoever you're working for your observations, and they go, "That's really interesting. I think you should do more experiments." So sometimes you may have to revise your hypothesis, come up with a new one, which will then lead to more experiments being done and more observations and more experiments. It sometimes can be a vicious circle, if you will. But ultimately, at some point, what will happen is hopefully it will lead usually to one of two things. It might lead to either a theory or it may lead to a law. And there is a difference between these two things, and we'll talk about it here. Theory is something that may not be correct in all aspects. It is something that maybe at one point in time, or maybe they didn't have enough information to truly discover these things. At one point in time, maybe it was thought that, these things are correct. And it can be later proven through experimentation that, well, maybe it's not so correct, or maybe part of it is correct. So for example, like the Bohr model theory of the atom works really well for hydrogen, but as you move away from hydrogen, it doesn't work so well. So, works good to explain what happens with hydrogen, but not so well with everything else. So it can't be used as sort of a general sort of explanation of what happens with everything. Dalton's atomic theory. There are certain parts of Dalton's atomic theory that are still correct today, and there are certain parts that are incorrect today. So theories are things that tentatively sort of explain things, but can sort of be revised, revisited. Further experimentation may lead to a discovery that maybe it's all not so correct. A law, on the other hand, is something that pretty much just always happens the same way, no matter what the situation is. So for example, if you have like the conservation law of conservation of mass, that means we don't really create nor destroy any matter in a chemical reaction. And that is why we balance equations, because, for example, if we started with 5 carbons at the starting of the reaction, we should end up with 5 carbons at the end of the reaction. Those carbons may be in different things at the end, but we still have 5 carbons. So if we start with carbons that each one has a mass of 12 grams, and we end with 5 carbons, although they're in different things, they still have a mass of 12 grams. We have the conservation of mass that always occurs because there are carbons basically on both sides. Conservation of energy, law of conservation of energy. Energy is thought of in most cases as being sort of like a nice perfect exchange, which means if somebody loses a certain amount of energy, somebody else has to gain the exact same amount of energy. So, if we had like a hot piece of metal, it's going to be giving off energy, right? Exothermic for the metal, right? It's hot. It's giving off all that heat and energy. For the metal, it would be exothermic and then like a negative value of energy being released. The surroundings, so where that metal is sitting, right, is going to pick up all that energy is being released into the surroundings. And for the surroundings, it would be a endothermic process, right? It's going to pick up the exact same amount of energy. So there's sort of this perfect exchange of energy that we think about, which is the law of conservation of energy. The classic example, potential energy, right, which is the giant boulder on top of the hill, right, it's about ready to fall over, turns into kinetic energy, right, as it falls over, which is the energy of moving. hits the ground, hopefully nobody's underneath it, right? Transfers all that kinetic energy to potential energy, right? And transfers all that energy to the ground, right? So all the energy can be accounted for, right? As it goes over the hill and starts to travel. So laws are pretty much these things that have been determined. You know, it just really always sort of happens this way. There's kind of like no exceptions, if you will. If you have that situation, it's going to occur. Again, theories are a little bit different than that. Theories can last for a really long period of time, and they can be correct, but they can be revised as further experimentation sort of occurs. That's sort of what we talked about here, our sort of scientific method. And again, as you can see, it can be a roundabout sort of situation, but hopefully, again, at some point, a theory or a model or a law sort of comes out of that. And as you can see here on the theory side, can have some modifications that can occur over time. Any questions on that there? All right. And those are, again, all the kind of things that we talked about here, I think. All right. So pretty much from chapter 1, that's all you need to know. Not much going on into chapter 1. So 1 down, 16 more to go. There we go. We're going to do it all today. There we go. We're just gonna knock it all out today, and just awkwardly stare at each other for the rest of this period, I suppose. All right, so we're gonna roll to chapter 2, but from chapter 1, you really just need to know a little bit about the scientific method, a little bit about that matter stuff that we talked about. We're now gonna really roll into the heart of the start of this class, which is measurements, and we're gonna talk about measurements here, how to take proper measurements. How to do conversions, dimensional analysis, density, temperature conversions, and all these type of things. So let's start with the basics here, which are units. And units are really important. Whenever you take a measurement, you should always have really a number and a unit associated with it. For example, if I wrote 225, what am I talking about? I have no idea. I'm hoping I'm talking about money, to be honest with you, right? I'm hoping that's like $225, but in my luck, that might be 225 pennies. I would still take it. It's still 225 pennies. You go through the drive-through. Here's my pennies to pay for it. But without any type of unit, a number is really useless. So whenever you take a measurement, you should always have a number and a unit associated with it. So we'll go with grams, for example. And then people really do have a reference point as to what that number represents. We talked about it the other day. Again, a reminder that as we go through this class, they do want you to be very prepared for 1A and 1B, which means, again, you do need to know formulas as we go through these chapters. You do need to know conversions as you go through these chapters. They expect you, when you do any type of calculation, to do it a certain way, which we'll talk about. And they also expect you to always make sure you have units when you give measurements and stuff like that. So again, these are things that you do need to know as you kind of go through all these chapters. So when we talk about units, there's really 2 types of units that we do come across. There is the English system, which we use, and then pretty much everybody else uses the metric system. So we have that sort of combination of metric and English. And obviously, as the world got smaller and people started doing stuff across countries and stuff like that, obviously people are using different types of units. There could be some misunderstanding about what's going on. So in 1960, they had a conference on weights and measures. Sounds like fun. And they did propose basically a sort of standardized system of units that's used in science and especially chemistry. And that is what is sometimes referred to as the SI units, or the International System of Units. Truthfully, it is pretty much based off the metric system. So metric system kind of won. So a lot of times in chemistry, you'll see the SI unit is this or the SI unit is that. And that's sort of the standardized unit that is used in chemistry for certain types of measurements that we make. So let's take a look at some of those. When we measure mass, the kilogram is the SI unit. Length is the meter. Time is the second. Temperature, you might not be familiar with, but after you take chemistry, you definitely will be familiar with. Temperature is Kelvin. I would say 99% of every chemistry type formula that involves temperature, it needs to be in Kelvin. So it is like a unit that we use all the time. You almost cannot go wrong in a chemistry class if you're doing a calculation to make sure you convert your temperature to Kelvin. Pretty much every formula uses it. There's really only kind of like one or two that you could leave it like in Celsius, but everything else is Kelvin for the most part. The amount of something we'll talk about in a later chapter is sometimes referred to as a mole, M-O-L or M-O-L-E, is the amount of something. So these systems and units are based off of sort of the metric system. It is really important as well, and what a lot of people sometimes struggle with is they really don't have an understanding of what a unit represents. So for example, I've had people come up and go, yeah, the mass of my thing was like 55 milliliters, and milliliters is a volume, not a mass. Or, my volume was 125 kilograms, type of thing. So it's really important if you're not sure, make sure that you do have an understanding of, when you're talking about something like grams, that's a mass. You're talking about something like liters or something like that, that's a volume, so that you clearly understand what those things are. So you don't get into any of those spots. So let's talk about mass, length, and volume. We'll first talk about length, and the meter is a very common unit that is used. Other common units of length are centimeters, kilometers, decimeters, but not so much. But I would say for us, kilometers, centimeters is used a lot. So 1 centimeter is 0.01 meters. 1 kilometer is 1,000 meters. That is definitely a couple of conversions that you will use a lot. Another version of this, of the 1 centimeter, is 10 to the minus 2 meters. You divide 10 to the minus 2 to both sides, gives you 100 centimeters is 1 meter. So you can use either of those conversions. Some people like to use the larger conversions rather than like the 10 to the 3 or 10 to the minus 3 or something like that, but they are the same. So I definitely would say you need to know, centimeters to meters conversion. Kilometers to meters is something that you use a lot in chemistry, and you should know that. Speaking of those prefixes, this is commonly used prefixes with the metric system to sort of change the value. And I would say probably most people always do this incorrectly backwards when they go to this table. So to make sure you do understand it, let's talk about it. And if we look at this column here, that is sort of like, for example, if we took kilo, is 10 to the 3. 10 to the 3, by the way, is 1 times 10 to the 3 in scientific notation. But 10 to the 3, what this means, for example, is if we take a look at, say, meters and kilometers, right? So kilometers and meters. The base unit is meters in both of them. This is kind of like the prefix unit, right? And when you look at a table that contains something like these numbers here, what that number represents is how much there is in the base unit to one of the prefix units. So if I had 1 kilometer, that would be 10 to the 3 meters. So that is the proper way. Can't tell you how many people will go 10 to the 3 kilometers is, 1 meter, and always kind of reverse those two. So when you see that, it doesn't really matter the base unit. Prefix works the same. If I had 1 kilogram, how many grams would I have? 10 to the 3 grams. So base unit, prefix unit. So it doesn't really matter the base unit, it's really the prefix. It works the same for everybody. Definitely kilo comes up a lot. Centi, milli, not a ton in here, but occasionally nano and micro. when you take 1A, you'll see nano, micro a lot probably pop up, and maybe mega as well. So, but for us, definitely the kilo, the centi, the milli, we do see a lot. And again, that is the way that you use it. So for example, nano is 10 to the minus 9. That would mean in 1 nanometer, there would be 10 to the minus 9 meters. So that is the proper way to do that. So that 10 to the whatever on the far right of that table is always how much of the base unit for one of the prefix units. How we get sort of the larger values when we sort of look at something is, again, like I showed you on the other page, we had our centi here, for example, which is our 10 to the minus 2. So again, 1 centimeter is 10 to the minus 2 meters. And again, by dividing this to the other side, which is basically 1 times 10 to the minus 2, that is how we get our 100 centimeters is 1 meter. So this conversion and this conversion are really the same. It's just whichever way you want to kind of do it. So some people like the larger numbers to use as conversion factors. Some have no problem with the scientific notation sort of way. Whichever way you do it, maybe just stick with a one way so you don't get confused back and forth. That's how I do it. As you can see, kind of with the larger numbers, in some cases, the prefix has the larger number and one of the other numbers because we divided it out. Any questions on prefixes? Yeah. How would it change for? Yeah, so the little m here would be, for example, the prefix for milli, and you could have something like milliliters, right? You could have something like millimeters, right? You could have something like milligrams. So you would put the prefix here. Liters would be the base unit, meters would be the base unit, and grams would be the base unit in that case. Is that your question? Yeah. So these symbols are used, in place of obviously the name. So if you had nanometers, kind of like what I did here, that is sort of what the N represents there. So usually if it's sort of a prefix unit, the first letter is the prefix, the second letter is like the abbreviation for the base unit as you look through it. Other questions? Yeah. No, it should just be for kilograms. It would just be kg in most cases. Yeah. So usually most unit prefixes, and there are some variations in some books, but in most people and how they do it is usually a kind of 2-letter sort of abbreviation, where again, the first letter is usually the prefix sort of abbreviation. The second one is the abbreviation for like the unit and the base unit. Yeah. Other questions? Now, there are some books that will do something like that. For example, I teach another class where in that book, they do something like milligrams is like MGM or something, so it's like 1,000 letters or something like that. But most people will do like 2 letters, and that's usually the rhythm of how it goes. Other questions? Okay. That's a ruler. Good talk. But this is a conversion between some different units. The inch is the English R sort of unit, and the centimeter is the metric system. And that is a conversion that, they always want you to know. I'm not sure how often you ever use it, but it's like everybody's go-to. Do you know the conversion between those? So that is 1 inch is equal to 2.54 centimeters. And that's an exact sort of conversion between those two. And obviously we have, while we're looking at this, that is a ruler. Yeah. And up on top is inches. Yes. On the bottom there are centimeters. Where do I find millimeters? Another ruler. Millimeters. Yes. On the bottom. Yeah. Little guys. Yes. 10 millimeters in a centimeter. Yeah. So 10 little dashes gives you 1 centimeter. It's good to know where millimeters are in case you've ever. So big numbers, centimeters. 10 little dashes, 10 millimeters in 1 centimeter. 1 inch is 2.54 centimeters and stuff like that. So when you do use a ruler, you always want to make sure that you are using sort of the correct side. Yeah, depending on what you're trying to measure it in. Obviously, if you're measuring inches, you would use the top. You'd measure in centimeters or meters, you'd use the bottom there of the ruler. Any questions on that? So there should be like 10 millimeters in 1 centimeter for those little guys. All right, we'll get back to taking measurements in a bit. Let's talk a little bit about volume. Volume is the amount of three-dimensional space occupied by a substance. The SI unit for volume is meters cubed, although most people don't use that. Most people will use either milliliters or liters as very common units. So 1 cubic centimeter is equal to 1 milliliter. So that's an important conversion. And there's really a few different ways that we can get the volume of an object. For example, if it is a liquid, probably the easiest way would be to put it into something like a graduated cylinder, professionally drawn there, and just take an actual volume reading. So you look at it, you look at the scale, you just say what the volume is. Now, sometimes if we want the volume of something that's a solid, like a cube, if we had like a cube, we could actually take several length measurements to help us get to the volume. So we could take the length times the width times the height or thickness. And if we measure each of these individually, that would be like a centimeter, for example, a centimeter and a centimeter. Each of these individual measurements are length measurements. But when you multiply them together, centimeters times centimeters times centimeters, you get what is referred to as a cubic centimeter. And a cubic centimeter is a volume. So that's a very common way. You'll do it in the first couple of experiments. You'll take a wooden block and you'll measure length, width, and height, and you'll multiply them together and be able to find the volume of that wood block, which is a very common way. Another common way we'll talk about is sort of a displacement way to figure out the volume. So one relationship that you definitely should know is 1 cubic centimeter is the same as 1 milliliter. And sometimes a cubic centimeter is abbreviated CC. Perhaps you heard that on a medical show. Give this guy 5 cc's before he dies. That's like 5 milliliters, basically. Yeah. So in medicine, oftentimes we'll use cc's for cubic centimeter rather than cm cubed in that case. Another really important conversion that you do need to know is the bottom one. We use it all the time. So very commonly, the way that we measure volume is in milliliters, and a lot of times we may need it in liters or vice versa. So 1 liter is 1,000 milliliters. So that is a very, very common conversion. So you definitely should know these guys. Another important sort of aspect of measurement is mass. And mass is the quantity of a matter that is present in an object. We oftentimes will measure mass using a piece of equipment like this, which is what is referred to as a balance. And that is a fancy word for a scale, basically. And when we talk about matter, which we just talked about, again, is anything that occupies space and has mass. The fundamental unit of mass is kilograms, and 1,000 grams is a kilogram. And that is definitely something that we use a lot. Milligrams, so kind of like milliliters, 1,000 milligrams in a gram is another one. And kilograms, right, which is our 1,000 down there, grams is a kilogram. So those are two very common sort of conversions that we use for mass. When we do use a balance, that is the process of weighing something. And when we weigh something, that is the process that we use, but you should refer to it as the mass. And there is a difference between mass and weight. Weight takes into account the force of gravity, mass does not. So when we do weigh anything in chemistry or most sciences, we do refer to it as it being the mass of the object rather than its weight. So if you weighed yourself here but weighed yourself on the moon, you would weigh differently because of the force of gravity exerted on it. That's basically what that says there. So weight involves the force of gravity. Mass is sort of independent, so we do refer to things as masses. So as you go through your chemistry career, make sure that you do refer to it as a mass. Otherwise, people start yelling at you. It's not the weight, it's the mass. Now, let's talk about first several sort of conversions that we're going to talk about. And this is the temperature conversion. And there is 3 major temperature scales that we deal with in chemistry. That is degrees Celsius, degrees Fahrenheit, and our friend Kelvin. Now, the first major difference between these 3 is you can see in the symbols, it is degrees Celsius, it is degrees Fahrenheit, but it is just Kelvin. So we don't use the little degree symbol, which is the circle to the left. We just call it Kelvin. And the difference between sort of how we convert these 3 different temperature scales is based on really where water sort of boils and freezes. So water boils at 212 degrees Fahrenheit and freezes at 32 degrees Fahrenheit. That is what we use to like take our temperature and stuff like that, where it kind of freezes and boils. The Celsius scale, which is the metric system, and that is definitely something that you should know. Water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius. That is its normal boiling point and freezing point. And you should definitely know those numbers as it comes up a lot. So you should know water, again, boils at 100 degrees Celsius and freezes at 0 degrees Celsius. By the way, when we were talking earlier, when we take something from, say, solid to liquid, liquid back to solid, that is the process of melting and freezing, depending on which way you're going. Does melting and freezing occur at the same temperature or different temperatures? What do you think? The 50-50 shot. So melting and freezing, same temperature or different temperatures? It actually occurs at the same temperature. So for example, 0 degrees Celsius for water is where it both starts to melt and actually starts to freeze. And it's really not until you get a little bit above 0 degrees Celsius that you have liquid water, a little below 0 degrees Celsius that you have basically ice. At exactly 0 degrees Celsius, you have basically both things happening at the same time, like ice crystals. You have some solid, you have some liquid water. I know it blows the mind. So you have both of those things in phases with each other. And then what determines which way you go actually has to do with the energy we were talking about. So if I'm at 0 degrees and I continue to put heat and energy in, what should happen? It should start to melt, right? And go to the liquid phase, right? If I'm at 0 degrees and I continue to take energy out, everybody's going to slow down and come together to the solid state and start to freeze. So the melting point and freezing point of a substance is really the same temperature. Is dependent on sort of what's going to happen as to what you're doing in terms of the energy, as to which way you go. Same thing happens when we get up there between liquid and gas and liquid. Condensation and evaporation happens at the same temperature as well. And for water, that's 100 degrees Celsius, which is the normal boiling point. At exactly 100 degrees Celsius, you still have both things happening. You have some steam, for example, you got some liquid water happening. Again, when you go a little bit above that 100 degrees, you got all that steam. When you go below 100 degrees, you would have that liquid. And again, depending on the energy you do as to sort of which way you would go. So these transition of states do occur at the same temperature, and that energy is really the determining factor as to what will happen. A third type of temperature scale used to be called the absolute temperature scale. It was later renamed for Kelvin, Lord Kelvin, as the Kelvin scale, and water boils at 373 Kelvin and freezes at 273 Kelvin. The way that we convert between these different temperature scales has to do with the differences in the temperature. That's about 180 difference there. And down here is about 100 units of difference. And that's really sort of how we build in the conversions as we go from one temperature scale to the next. And that's sort of what this picture shows. the different scales and sort of the differences between it, 100 units and 180 units. So let's talk about how we go about converting our temperature values. I would say outside of chapter 2 and most of your chemistry journey, pretty much the first one here is the one you're going to use most of the time. And that is most of the time you need to take the temperature in Celsius and convert it to Kelvin. And to do that, it is 273 plus the temperature in Celsius. The true number is actually 273.15. Most people do not use the 0.15 because it usually gets rounded off anyways. So I personally use 273. Most people use 273. But if you want to use 273.15, you can. The other thing that we do probably a little less often is convert our temperature from Kelvin back to Celsius. So it obviously would be the opposite of that calculation. Our temperature in Celsius would be our temperature in Kelvin minus a 273. The other conversions here is going from Celsius to Fahrenheit. The temperature in Fahrenheit would be 1.8 times the temperature in Celsius. So 1.8 times the temperature in Celsius plus a 32. That 1.8 is the 9/5 that maybe you learned as a fraction to convert temperature. And if you want the temperature in Celsius is the temperature in Fahrenheit minus 32 divided by 1.8 as well. So if you want to go from Celsius all the way to Kelvin, you got to kind of do the Celsius to Kelvin conversion. But if you want to go from Fahrenheit all the way to Kelvin, you got to go from Fahrenheit to Celsius, Celsius to Kelvin. Outside of chapter 2, probably won't see very much of all the bottom one, but you still need to know how to do that conversions or those conversions as well. Now, when we do give answers, we do want to give it to the proper number of significant figures, which we will talk about significant figures a little bit later on in this chapter. But when we are doing simply just a temperature to temperature conversion, so taking a temperature value from one unit to a temperature value in another unit, there is sort of a special rule that most people follow in terms of significant figures, in terms of how your answer should look. And that rule is this: if you're strictly just doing a temperature to temperature conversion, you make your converted value look like your original value. And what that means is if your original value was a whole number, when you do the conversion, you just take your converted number to a whole number. If your original value went to the first decimal place, you should take your converted value to the first decimal place, and 2 decimal places to 2 decimal places. That is just so we're clear, specifically and only for when you do temperature to temperature conversion. So that's the general rule you should follow. We will talk about later on when you're not doing temperature conversion, just doing calculation, what rules you should follow. But for temperature, that is what you should follow. All right, so grab your calculator, do these conversions, see what you come up with. Make sure you remember where your calculator is at. I would also remind you to bring a calculator, since we will do lots of calculations in the lecture. And by the way, for lab days as well, you would need a calculator. Yeah, let's take a look and see. So the first one here, we have Celsius and we want Kelvin. So that is our temperature in Kelvin going to be our temperature in Celsius plus a 273. That will get us 28.5 plus a 273. And a 301.5 Kelvin. Once again here, no degrees on the Kelvin, and our original number went to 1 decimal place. Our converted number also went to 1 decimal place. So again, with temperature conversions, that is what you're looking for. Yeah. You can use that, but most people don't use the 0.15. And there's nothing wrong with using it. It actually is the really official number. But over the years, most people usually take it off because a lot of times it'll kind of get rounded off a little bit along the way. So if you use it, it's okay. And if you got a slightly different answer, if you did use it, that's okay. But most of the time, most people will use just the 273. Other questions? Okay, so let's take a look at the next one, which is degrees Celsius and Fahrenheit. So temperature in Fahrenheit equals 1.8 times temperature in Celsius plus a 32. That means 1.841 plus 32. So 1.8 times 41 plus a 32 gives me on my calculator 105.8 degrees Fahrenheit. Should I leave it at that answer? In this case, I should not. My original number here is a whole number, which means I do actually want to take this to a whole number. And I have an 8 that comes after a decimal, which means I should round up, right? So this would be 106 degrees Fahrenheit. Again, original number, whole number, converted number here for temperature ends up as a whole number as well. Any questions on that one there? And coming down here to our last one, we're going basically from Fahrenheit to Celsius. So Celsius would be our temperature in Fahrenheit minus 32 divided by 1.8. And that's going to be a $1.60 minus 32 divided by 1.8. That's going to be 160 minus 32 divided by 1.8. That's going to give me a 71.11111 degrees Celsius. Now, I know you would never give me that many numbers, right? So don't ever give me that many numbers. Wrap it around the next page. And I say this is not a joke. I've seen it. I had an answer once on the test. It went this way. He ran out of room, wrapped all the decimals around the next page. So we want to make sure, again, we end up at the right one. In this case, if we look at this, that is, again, a whole number. So really here, we should end up there at that whole number. And that would be 71 degrees Celsius. Any questions on these temperature conversions? Once again, you do need to know these formulas and how to do these conversions. You need to know how to do all these conversions. And again, after chapter 2, pretty much you're going to be using that Kelvin and Celsius conversion probably most of the time, if not exclusively, probably all the time. And occasionally going the opposite way, a Kelvin back to Celsius. So that was kind of back and forth is really the one you should definitely commit to memory, but you should know them all for sure. Any questions? Okay. All right, as we talked about before, it's really important to also know when you do look at a unit, what it is representing, so that when you say something, you know, it makes sense. So we know, right, Kelvin is a unit of temperature, right? Liters is a unit of volume. Meters is a unit of length, right? And kilograms is a unit of mass, yeah. So I will not hear anybody tell me they have, 532 grams of volume of water, right? All right, very good. All right, so speaking of measurements and taking measurements and maybe different ways to classify these type of things, that brings us to qualitative and quantitative. When we talk about something being qualitative, that's really consisting of sort of general observations about something. It's really not measurement based. So when you do a qualitative sort of observation, it's really not a measurement that you're taking. You may say, hey, it turned purple, there was rainbows, maybe unicorns, whatever it may be. There was some steam that happened. That's all qualitative. Now, different than that is quantitative, and quantitative, it's all about the measurement. So quantitative is measurements have been taken, hopefully pretty good measurements have been taken. They have units associated with it. So for example, if you were doing an experiment and you needed 5 milliliters of water for sure, you would do a quantitative type of measurement, right? You would get a graduated cylinder or something like that where pretty sure that you got 5 milliliters of water. If you weren't that interested necessarily in getting exact amounts of things, which by the way, does occur in lab experiments. And if you take Chem 1B, you'll do a ton of labs, which are called qualitative analysis. And I'll say I feel bad for you now because there's a lot of stinky sulfur stuff in those labs. They put you in a fume hood, but it still stinks. But in those type of experiments, you really don't measure out anything, even though it says, hey, you need like a milliliter of this. What you do in those type of experiments is, because it's more qualitative, it doesn't really matter if you miss it by a drop or two. You go, okay, like 40 drops is a milliliter or something like that. You don't really measure it out with graduated cylinders or anything like that. You need a mass of some type of solid. You don't measure it out. You just kind of take like a spoonful of it and kind of dump it in. So qualitative actually does occur in experiments as well. And like I said, in Chem 1B, there's a ton of qualitative experiments where you're not supposed to measure anything out. You're just kind of supposed to add, because it really doesn't make a difference, and it allows you to do the experiment and it will come out the same as if you measured out if you didn't. There are certain things where it's really important, right, to get the right amount of stuff. And those are definitely places where you want to be quantitative and make sure that you do measure things out. Any difference? Question on the difference there? Yeah. Yeah, quantitative really is any type of measurement. So, in the aspect of a lab, if you were doing a lab and you needed to measure out a certain volumes of a liquid and you want to do it quantitatively, that means that you really should grab the right piece of equipment that you could take a really good measurement to know, hey, I got 5 milliliters here, 2 milliliters here, and stuff like that. If you were doing the experiment where it's just like, qualitatively, get yourself 5 milliliters water, you may just grab a beaker and go to like the 5 mil line or half of the 10 mil line, which if you ever know, or what you will learn, is a beaker is a really crappy piece of equipment to measure out volume in, because you'll never get close to what you're looking for. But if you want in the ballpark, you just kind of fill it up somewhere around that 5-ish mark where it may be. And yeah, it's maybe 5, but maybe it's really 7, or maybe it's really 3, but you're in the ballpark. It's more qualitatively. So a lot of experiments that we do, obviously in this class, is more quantitative. When you're doing the experiments, you want to make sure that you're measuring everything out correctly. But there is a whole actually field of chemistry which is qualitative, where, it doesn't really make a difference, that you measure out everything. You just got to kind of get everybody together in the same test tubes for the reaction to occur. Other questions? All right, so let's talk a little bit about scientific notation, which is an important way that we sometimes represent numbers. So a lot of times in chemistry, we do come across a lot of numbers that are really large and a lot of numbers that are really small. And obviously something like that first number there is 602,000. I don't even want to count all those zeros. Avogadro's number, I think. That's a lot of zeros. So if I try to write all those zeros down and use it in calculation, there's probably a fairly good chance I'm going to lose some zeros along the way. And same thing with the second number, which is a really small number, right? 0.000000, like 166 there at the end. That's a really small number. So to handle those, we use scientific notation. And scientific notation is n times 10 formula. This n is a number between 1 and 10. So that very first number, when you write it in scientific notation, does need to be a number between 1 and 10. It cannot be 10. That also means I cannot write a number in scientific notation as like 125, because that's clearly above 10. I cannot write a number correctly in scientific notation as like 0.25, because that is less than 1. So it has to be a number between 1 and 10, that first one. Yeah. It can't be 10. So it has to be a number between 1 and 10. So it's got to be, like 1 point something, 9 point something, 8 point something. So it's got to be a number that falls in there, and really not 10 either. So it's got to be between that number. Yeah. It can sort of be 1, and it'll be a sense of like 1 point something. So it can be 1, but it has to be not really 10 usually. So it's got to be a little below 10. And it's times 10 to this little n. And this little n is going to be either a positive or a negative kind of whole number. And it really is going to be dependent on sort of how many decimal places you had to move to get to that number between 1 and 10. So if I had a number that was 1, 2, 3, 4, very creative, and we wanted to turn this into scientific notation here, although there's not a decimal written, we would assume obviously it's at the end there. So if we go just one place over, that's 123. That is not between 1 and 10. We got to go one more place. That is 12 point something, which is not between 1 and 10. We got to go one more place. That's 1.2 something, right? And that is a number between 1 and 10. So this would be 1.234 times 10 to the 3. I moved the decimal place 3 places to the left. It gave me a positive 3. Now, if I had a number such as this, 0.0256. If I move the decimal place one place here, that is not a number between 1 and 10. That is 0.2. I gotta go one more place, gives me 2.56. That would be 2.56 times 10 to the minus 2. It is a negative number because I moved the decimal place to the right. Good way to remember that is the top number is a large number, right? Bottom number is a small number. Large numbers have positive exponents. Yes, small numbers have negative exponents. So the number is obviously how many places you move the decimal place along the way. Question on that there. Now, speaking of writing something in decimal form, this is also really important, is putting the 0 before the decimal point. You should always do that. You should not just go 0.0256 because as you do calculations and use them in calculations, without that 0 before the decimal point, before you know it, all your numbers run together. Not sure which number is which. Yeah, so that 0 allows you to separate out, and it is good practice, especially in chemistry, to always keep that 0 in front of the decimal place so you can clearly separate out your numbers. Any questions on that? Scientific notation is really important because it does help us in some cases. And I will say for me personally, you do not necessarily need to write every number in scientific notation. I don't really care if you do or not. You could write it in decimal form, which is sometimes referred to as positional notation, or you could write in scientific notation. You would need to write in scientific notation clearly if the instructions said, put it in scientific notation. The other place where you would have to perhaps use scientific notation is there may be the only way for you to get the proper number of significant figures when you do a calculation is to write the answer in scientific notation. And in scientific notation, you could kind of control how many significant figures you have. And that is because when you write a number in scientific notation, all of the numbers that come before the times 10 part are significant. And they're significant figures. That means that this number here would have how many significant figures? It has 4. There are 4 numbers before the times 10 part. This number down here would have how many here? It'd have 3. Those would all be significant. By the way, this number had 4 significant figures there. So does it have 4 significant figures when it goes into scientific notation? This number has 3 significant figures. It should also have 3 when it goes into scientific notation as well. You should not lose significant figures as you go from scientific notation to decimal form and back and forth. And we'll talk again how to identify all those things. So why is it important and why you can do it? Let's just say, for example, I needed 4 significant figures on this number rather than 3. I could just simply go 2.560 times 10 to the minus 2. This now has 4 significant figures, right? I could keep adding zeros to however many significant figures I need. So even if I needed, say, only 2 significant figures, I could drop this to 2.6 times 10 to the minus 2. Now I have 2 significant figures. So using scientific notation can, in certain cases, you may come across a problem where there's just absolutely no way to keep the proper number of significant figures in decimal form. You've got to use scientific notation to do that. Any questions on that there? Now, clearly, when you go the other way, you do need to be able to go backwards. So if you do see something like 1.25 times 10 to the minus 2, and you want to convert it into decimal form, the minus should tell you it's a small number, and the only way to get this guy small is to go to the left and put zeros, right? And that would get you 0.0125, going the opposite way. And same thing if you had 1.25 times 10 to the 3. 3 means positive, big number. Going this way will make us a big number, and we'll end up with 1250, I think. When you convert it. So you do need to be able to write it properly in scientific notation, and you need to be able to take it from scientific notation to decimal form or positional notation. Any questions? So let's talk really more importantly, perhaps, which is scientific notation in your calculator. And most people do not know how to properly punch it into their calculator, a number in scientific notation. And if you plan on taking chemistry courses like this course, and 1A and 1B, you definitely should figure out how to do that correctly. So let's talk about how to punch in your calculator scientific notation. On most scientific calculators, there is actually an exponent button. And on most calculators, it is either an EE button, an EXP button. And if you have some of the newer calculators, a times 10 to the N button, these are usually like the two-tone type calculators. It's like one color in the center and the outside is kind of a different color. They usually also have like a little wheel on it as well. So if your calculator has that, we'll talk about what you need to do in a second. And these are all exponent type buttons that you find on a calculator. In addition, the other button that's important is the negative button. And on most people's calculators, that is the negative button, or it may look like this. It is not the subtract button. So, one of those two buttons. You do not want to use the subtract button as your negative button. So let's just say, for example, we wanted to punch into our calculator 4.25 times 10 to the minus 6. So if we were going to punch this into your calculator, this is how you should do it. If you want to punch it in correctly, which I assume you probably do. So you would type 4.25. Then you would hit your exponent button. So either this button or this button. We'll talk about this guy in just a second. And when you do that, what you should see on your screen, and by the way, no multiplication or anything, just the exponent button at this point. You will see on your screen usually 4.25 might pop up an E. You may see 4.25 may pop up a couple of zeros, maybe be like a times 10 on the bottom and a couple of zeros up on top. When you hit that exponent button, this button represents this part of the number, the times 10 part of the number, which means you do not need to hit the multiplication button. You don't need to hit what most people like to do, the like shift or second and log button. You should not be using those buttons at all when you're doing this. So what is left now is really just the -6 part of the number. So we again want to use our negative button. So you would hit your negative button, one of those two. It would put a negative there, put a negative there. And what's left is 6. So you would hit 6, it would put a 6, it would change that to a 6. And that would be the proper way to punch into your calculator 4.25 times 10 to the minus 6. At no point, again, do you hit the multiplication button. At no point do you hit like the log button or inverse log. If you're doing any of those things, you're really punching it in incorrectly, and you will run into some trouble later on in chemistry, and especially in this class as well. The way you can kind of know that you're not really punching it into your calculator correctly is when you do get the answer, it's really close. Like the first part of the number looks all good. And then when you look at the times 10 to the whatever, it's like off by 1 or 2 or something like that, usually 1. And that's because you really didn't punch it in correctly. So you want to make sure whenever you have a number that's in scientific notation, you use the exponent button to do so. Now, if you happen to have the calculator that has this button on it, and there are two separate buttons, but mainly the exponent button really is this button here. You have to do a couple of things because of the way those calculators are really programmed. You actually have to put a parentheses. So you have to open a parentheses. And then you would do everything very similar. You would hit 4.25. You then would hit your times 10 to the n. And what it will show you on the screen is parentheses 4.25. It will put 10 times 10, and you'll have like a little blinking cursor kind of blinking up there up on top. At that point, you could kind of put the rest of it in. You could hit your negative button, whichever one you want to use, and you could hit 6. And what it will then go to is 4.25 times 10 to the -6. And you will now still have the little blinking cursor next to the 6 at this point. The problem is at this point, you need to close the parentheses for your calculator to do it correctly. And if you just hit closing the parentheses, it will close the parentheses like up here. And on some calculator, it'll go error. You punched it in wrong because the parentheses is way too high. It shouldn't be there. So what you have to do kind of most of those calculators is instead of just closing the parentheses right away, you need to go to your wheel that you have and you need to really punch that side of the wheel. And when you hit that side of the wheel, it will bring the cursor down to a regular size and you'll have something that will look like this. And now the cursor will be kind of blinking like normal. Now you can close the parentheses point and you'll have a number on your screen that looks something like this. So if you do have that times 10 to the n button as your exponent button, it works fine. You just have to really put parentheses around all the numbers if you're going to put in a scientific notation. If you don't put the parentheses, you're going to end up with the wrong calculation. The calculator will actually break the number up into separate numbers. It'll do the math wrong and you'll end up with the wrong calculation. Any questions on that? All right, we will do some examples of calculations next time. And again, if you're not sure where your exponent button is at some point, come see me. We'll figure